All right, I'm sure you all enjoyed your weekend away from math, but we just have this lecture and one more lecture to go, and that would actually conclude our first series on AP Calculus. Pretty good, right? Okay, so let's get back to business here on our next topic of integration. So, we still have one other step to do. Now we're expanding this to the reciprocal trig functions. So these guys are what I like to kind of describe as the second half of trigonometric functions for us. And of course, that would include all of your good boys like secant, cosecant, and of course cotangent. These guys now have their own integrals associated with the rules of those functions. But unlike the first set of our basic sine, cosine, and tangent, these guys will have separate rules which are not going to always be simply, for example, the integral of secant of, let's say, x. This guy is actually kind of a problem in integration. But nonetheless, we still have other rules involving these, which we will still need to get accustomed to, such that we can still solve problems on the AP exam. So why don't we begin with some rules? So we have our rules here. Let me just number them out one at a time. Starting with the first rule, we'll go with something that is quite simple and quite similar to what we've dealt with, is going to be the cotangent. So the integral of cotangent of u inside of that function, and that will result in, instead of what we did with tangent, we are simply going to switch it around. It's going to be the positive natural log of the absolute value of sine of u plus c, all in the absolute value. Or we can also write it similarly as we did with the tangent. We can write it as the natural log of the cosecant of u inside of that plus c, but we do need to keep track of a negative sign in there as well. So a little bit of a switch around with the normal way that we've done it before with the tangent, but that is the first rule, and I believe the most similar rule to the rest of the trig functions. Now we have the next issue, is that because we have the main problem that secant and tangent aren't exactly one-to-one, we have to remember the integral now instead of secant squared of u du. That is going to be our most similar secant rule, because the secant squared will then go backwards into a tangent to the first power of u plus c. Okay? Now similarly, we also have the same idea this time if we had cosecant as well. Those two go hand in hand. We square that. And so this guy, cosecant squared, is going to give us cotangent of u plus c. Now, of course, if we picked up on the patterns, with that co in the name there, we will have to put a negative as the result of the integration. Now, how in the world do we get these though? All right, where did these come from and where did they go? Where would they come from? From these derivatives, of course. These derivatives are going to be, of course, the basic rule that by taking the tangent and that derivative, again, we're going to take this one step backwards instead. That's how I get secant squared of u, right there on that side. So, given that we can only take the derivative from tangent going into secant squared, of course, that's going to be quite the same with the cotangent on the other side as well, giving us negative cosecant squared of u du. Now, of course, to make it match 100% is that negative sign on the cosecant, which was not on the integral, just simply needs to move over to the other side as negative cotangent, and that derivative will then give us the positive cosecant, just to make sure we've matched up everything 100% on this derivative rule. Not terrible, but still it is going to be actual steps we need to take and rules we need to remember on how to take those integrals. All right, and looks like we have one more to go, and that should really wrap up all that we have on these topics of the reciprocal functions. So now we get to transition over to what we call a little bit of a mess, but still it makes sense when you really think about it. So if we then took instead the integral of secant of u times the tangent of u, this guy, now again, thinking about going in reverse, is going to be just secant of u plus c, okay? And again, similarly, if you go in the different vein here as cosecant of u, and then the cotangent of u du, that will then give us instead a negative cosecant of u plus c. Now, remember, this is all still the same idea, is that we're dealing with these derivatives. So now we could only really match it up one for one if we take the integral of the result of the derivative of each of those reciprocal functions. For example, secant, that derivative is going to give us what we started with, a positive secant times a positive tangent, and then the derivative of the inside if there's any other chain rule to keep track of. And of course, on the other matter as well, if we have negative cosecant, starting with the negative, then that will slap on another negative after the fact, making it back to a positive cosecant of u times a cotangent of u du. So there are a number of things which we still need to keep in mind. All we really are doing with these guys are just building off of our memory of the derivative rules. And so by going backwards, we can at least remember that by remembering the derivative rules, we can go backwards with some integral rules, and that should make our lives a little bit easier. So let's quickly swap it over here. And so from this, we have one quick example we'd like to go over before we end today. So we have now the integral of 1 over sine squared of 2t times dt. This guy, though, we can try to use instead one of the rules that we learned today to make our lives a little bit simpler. So even before we go and make any other side notes with some rules to remind us, we can also simply switch that over to the reciprocal form of a cosecant squared 2t. Of course, hopefully we remember those days back in pre-calculus. But nonetheless, though, this is where we can take our note from. So to swap it over, and one of our strategies here is that if we take our notes to remind ourselves of the rules that we can use this time, that will really help us make some decisions on how to solve these problems. So as a note, again, our rule here that we just learned today is that we can take the integral of cosecant squared of u, and that will result in, again, cosecant squared means that it needs to be the derivative of the cotangent of u plus c. Now, of course, always remember that dealing with these co-businesses of these trig functions, we're going to need a negative on the fact. So the positive integral of cosecant squared of u will give us a negative cotangent of u plus c. Not too bad. So why don't we, again, as always, just take a quick experiment here just to see how our proposed answer will look like. So going with cotangent of 2t, again, are we going to check that to make sure that we've matched up everything from here if we take its derivative to go into there? So for those who want to just take this one step at a time, we can give this a go, and hopefully if everything else matches up, we can just slap on some coefficients and we can call it a day. So cotangent, now remember, some of you might have forgotten that we need a negative sign on the outside of that. Simple mistakes will lead us to big problems, wouldn't it? So with the negative there, we have a negative on the outside, then that derivative will go to negative cosecant squared of 2t. Okay. Now, again, we have chain rule coming up. So we need to go and take that derivative of 2t inside of the function down to the next level. So that's going to be multiplied by a positive 2 and then plus 0 for the constant. Pretty nice. So it looks like we did keep track of the negative sign, so that's very nice. Cosecant squared of 2t. That does match. The issue, of course, is now we have a whole positive 2 waiting for us. So, of course, all we need to do is to make sure now we need to multiply by a positive 1/2. This guy is going to be the real fixer to end us up with this problem. So, with that coefficient just remaining there, we can end up with a negative 1/2 cotangent of 2t plus c. Now this should match up with this. Again, this is now our second proposed answer. And as always, with every single one of our answers from an integral, we will be able to check it with another derivative to make sure everything here matches up with everything there. Let's try one more time. Again, we cannot circle our answers unless we're absolutely certain. And let's take a note of our check. We need to be absolutely certain that our answers will match exactly with the integral. So negative 1/2 cotangent, well, that's a negative 1/2 we can leave as a coefficient. The cotangent of 2t, thankfully, that still remains as cosecant squared of 2t. And then we have to slap on the negative there as part of the derivative rule. And then lastly, we need to multiply it by a positive 2 from chain rule. There you go. It looks like we got everything we needed. We got the negatives canceled out. We have the 1/2 canceled out with the positive 2. And would you look at that? Everything does match that. It's cosecant squared of 2t, all that matches 100% up in the integral at the start of the question. So there you have it. We can very easily box off that answer as indeed a tried and true response to that integral. Of course, this made our lives a lot easier given the fact that we can swap it to a cosecant thanks to our prior knowledge in pre-calculus to use some reciprocals and then our integral rule after that. Very good. So we are just about finished here. We'll do one set of examples tomorrow, and then by the end of the week, we will have finished our entire series on integration. So it looks like we are just one last step away from finally no longer being able to integrate into some lovely calculus students. We will see you then.